Richard Oaf, please join me on screen. Richard's a guy I've known for years at Core & Main. Richard, thank you for sponsoring today.
Yeah, thanks for having us. We're happy to be part of the Alliance. Been here a long time. Core & Main, I think you guys know, pipe, valves, and fittings, our specialty. And I happen to lead up the Fusion division on the West Coast. And we've got a ton of products regarding HDPE and specifically Electrofusion. So happy to be a part of the webinar today.
Yeah, well, as you've taught me over the years, Richard, it's not just Electrofusion. You know, the first thing that happens is the pipe, then the butt fusion, then the Electrofusion. It's not like they come to you and say, hey, I want Electrofusion. Is that right?
That is correct. Unfortunately, sometimes we don't have a choice with Electrofusion. We're thrown into it if there's been damage to a pipe, possibly a tractor or something getting into it. But always best practice is to consider Electrofusion as you're starting your layout of your pipe project.
Yeah, no question. Dan Landy.
Yeah, I didn't plan on getting into this at any direct point today, Richard, but I did get a question today on a large manufacturing plant in the Pacific Northwest. They're bringing on a 36-inch line here sometime in the middle of the summer. So they asked about availability. Is the availability of Electrofusion, are you guys stocking it or the manufacturer stocking it? I mean, how difficult is it getting product quickly on a job site?
Yeah, that's correct. And we stock 36-inch and down, and then several factories are stocking at both 36-inch. So a matter of a day or two or three, we could have some product on the ground.
All right, fantastic. Well, Richard, thank you so much for being here today. Pete, if you want to keep us rolling.
Yeah, thanks for that question, Dan. And that kind of brings up the point, Dan, of, you know, who is stocking all these products that the contractors buy. And, you know, I'll give you my take on that. And that is, you know, distributors like Core & Main are excellent stewards of the industry by committing millions of dollars to product in our industry. It's not unlike the ductile iron and the PVC industry. We're doing the same thing. But in the water industry, guys, we're the newer guy on the block. Of the 9 major markets that use pipe, we dominate 5.5 of them. We don't dominate the municipal market does, PVC does. So we're generally speaking, people don't know us as well. So we do have to stock material. So we do, and we're thankful for Core & Main for doing that. So also we've got Stephen Boros, who's a usual on this program. Welcome, Stephen.
Hey, Peter. How are you guys doing this afternoon? Glad to be here for another PE Alliance webinar. Appreciate you having me.
Yeah. Well, you're a pipe guy, but you're also an expert on Electrofusion. So we're excited to have you. Welcome back to the program, and please participate as you can. Bill Breckenridge, Strongbridge. You know, Bill, I've known you guys for a long time, and
Yes.
Talk about inventory. You guys have a lot of inventory too.
We sure do. We have 50,000 square feet of warehouse space in Jacksonville, Florida, from which we ship, and it's full of Electrofusion and molded fusion fittings.
And you're one of our experts today. Tell us a little bit about your career and how you came to get into the polyethylene world.
So it was random getting into the industry, but I've been here for 30 years in capacity of fabrication, sales, branch management, training, and now back into sales again.
Yeah, well, we're delighted to have you today. And you guys at Strongbridge have been a big supporter of the Alliance P Pipe, and we thank you. You know, Dan shared this with me earlier today. Stephen, if you wouldn't mind coming on, I did not know how to answer this question. I see a print line of a 3510. I think that might be a mistake, but Stephen, tell us, how would you answer this great Electrofusion question?
Yeah, that's a good point, Peter. So basically, yes, you can electrofuse and fuse to older HDPE materials. As far as I can know, has not been a 3510 resin. So that could have been a 3710 for a period of time, and we were transitioning from 3408 to 4710. There were some 3710 resins on the market. But anyway, you should know what type of material it is from the print line. So that's a good way to look for it. You can electrofuse and heat fuse in general to these older materials. Just remember, though, that surface prep is probably going to be a little more important. Make sure that you do it thoroughly, because what you're trying to do is remove that outer surface oxidation or contaminants. And of course, if it's an older material that's been in service for a while, you're going to have to remove that. If you're in liquid hydrocarbon service, there are a few other things you may need to be aware of, but that's a very specific issue. But in general, yes, you can heat fuse and electrofuse to older materials.
Yeah, so there's an old product out there in the early days called Aldol A, ALDYLA. That was a YL space A. That was a early generation product used primarily in the gas industry, and you're not permitted to electrofuse to that, correct?
That is correct. Yeah, and you're right. You will almost exclusively see that in gas distribution. It was installed from the 60s all the way into the 90s. So there's a lot of it out there. It has a very unique color. It's like a tan, fleshy looking color. Typically, there was some black Aldolay that was made in Canada for a while, but almost exclusively 99% of it in the gas distribution industry. You're right.
Well, I love talking to guys like you with that history. The reason I like this question so much, Stephen, is because it talks about the actual 4-digit number of the resin that was used to make the pipe. One of the key distinguishing features of the various pipes over time is that our pipe keeps getting better. And one of the ways we know which pipe it is by that number. Could you just give us a brief background on those digits, what they mean and why we should care?
Absolutely. Yeah, they do. I mean, they do mean a lot. So the people that know where they came from and how they're developed, they tell us a lot about the individual materials, and they have changed and evolved over time. PE 4710s are what we call the 4th generation polyethylene materials. So there's been really 4 major generational changes, and each one to improve performance properties of the material. So the first number in general has to do with the density. So we start off with 1404. So that's a 1. So that's going to be on the low density range. Then we went to like 2406s and then 2708s, the 2's medium densities. Those today are used almost exclusively for gas distribution. They're very good performing materials, been around for 50 years, but they still perform extremely well. Then you get into the high density materials, which used to be the 3408 type materials, 3306 and 3408s, and now 4710. So each material means a little something, each number means a little something different. The 4s are going to be a little bit higher in density. The 7 is really, really good slow crack growth properties, extremely good slow crack growth properties, resistance to cracking. And the 10 is the design stress in units of 1,000 or 100 PSI. So 1,000 PSI design stress. So it does mean a lot you can gather just from those numbers.
Thank you for that, Stephen. And if you do want to dive deep in that, we do have a bunch of YouTube content talking about those material properties of HDPE pipe. Yeah. So Dan Landy, thank you for bringing that to us today. All right, let's talk a little bit about fusion. Stephen, this is going to be you, right?
This is me. Yeah, you're stuck with me for a few minutes on your chemistry lesson for the day.
Take it away.
So let's get into polymer. So very simply, what is a polymer? So polymer and then monomer. Those are 2 terms you're going to hear very frequently in this industry. So poly, from the Greek word meaning many, of course, and mono, the Greek word meaning single or one. I feel like I'm on Big Fat Green Coretti and everything evolves from Greek. And there you have it. There you go. And meros meaning many. So there's where the polymer comes from. So the monomer is what we start with. So that's the single building block. Every polymer that's made starts with a single block unit, and then you join those into many, many blocks, depending on what you're trying to make and what properties you want, and then you get the polymer. So that's just very basically what you're looking at. Again, the polymer describes the chain that you end up with, made up of many, many, sometimes tens of thousands or even more, hundreds of thousands of these monomer units all linked together. So for polyethylene, specifically what we're talking about is poly and then ethylene. So ethylene in this case is the monomer. Ethylene's a gas. Actually, it starts from ethane. So ethane is what comes from hydrocarbon source. In the United States, it's almost exclusively from natural gas. As you know, we have a lot of natural gas in the United States today. And so ethane is extracted as one of the components of natural gas. And then ethane becomes the starting building block. We put the ethane, which is a 2-carbon chain with 4 carbons hanging off of it. Actually, 6 carbons, 6 hydrogens hanging off of it. And then you want to cleave that. So you cleave 2 of those hydrogens off, and then those two carbons had form a double bond. That double bond is then called ethylene. Just as it's a very common thing. You can use ethylene to make polyethylene, to make PVC, to make CPVC, to make all sorts of polymers from this simple building block. However, you have to do some other things to it. Just for instance, and that double bond is not as strong as a single bond. So you want to kind of break that bond and do something else with it. Just for your edification here, if you cleave another hydrogen off there, you form a triple bond, and then that's what we call acetylene. Acetylene, as you know, is very unstable, burns really hot, and that's when that bond is breaking. That's when you get this energy releasing. So that's kind of where we're starting with when you have these double bonded hydrocarbons or carbon molecules, and then you're going to throw those into a reactor. So when you take these single ethylene units, and then you're going to throw them into reactor. The reactors can be a big steel tube, essentially, that's circulating around. It can be a solution phase. It can be several different types. So essentially what you're doing is you're breaking that double bond from those carbons, usually with a activated metal ion of some sort that energizes it with an electron. It breaks that carbon double bond. And now those single carbons have a free bond they want to join something with. We call that a radical. Radical just means it wants to connect with something else, or it wants to make sure that it forms its lowest energy state. So when you throw all these together, you got all these ethylene molecules that now have a free hand, and they run around the reactor, and they randomly come across another one, and they grab hold of it. So that's when these ethylene molecules then start forming these long chains. So that's when we start forming polyethylene. Now, there's lots of different ways to join the polyethylene. There's thousands of different types of polyethylene. So in this case, we're going to be talking specifically about the kinds of polyethylene we use to make pipe from. These are very highly engineered molecules, very specific for a very specific situation and long-term performance properties. Some other ones that you might know are, polyethylene homopolymers. They're just made up of ethylene. That's it. Nothing else that's going on there. No what we call co-monomer that's added to it to give it different properties. That may be your milk jug resin. That's a very short-term type resin, high density, low slow crack growth resistance. It works really well for a few months as a milk bottle or a water bottle, but you wouldn't want to use it in a long-term application. So what we do is we join all these molecules together, and it doesn't really say that here, but what we end up doing is we throw a co-monomer in there too. This co-monomer kind of shakes things up a little bit. It makes these long hooks that come off the side of these long chains, or excuse me, small hooks that come off the end of these long chains. And these things make it harder to pull the molecule apart. And essentially what that gives you is more resistance to slow crack growth mechanisms. So anyway, you got all these polymer units now moving around in the reactor. This isn't what we would call a batch reactor. You don't throw a bunch of ingredients in, it all reacts, and then you take them all out. This is a continually stirred tank reactor, they call it. So you're constantly putting in ethylene molecules. They're in there reacting for a certain amount of time, and you're constantly taking polyethylene out. So you get what's called a molecular weight distribution from that. And we control that very specifically. What's the longest chain? What's the shortest chain? What's the average chain? How much co-monitor do you have into it? And that's what gives us this ability then to have a semi-crystalline material. That's what polyethylene is. It's a combination of both amorphous, which is no long-range order, and crystalline, which is long-range order. So where you don't have these side chain branches coming off from the co-monomer, it can pack really tight into these crystalline long-range order construction. When it comes across this side chain branching that comes off, that kind of moves things out a little bit. That becomes your amorphous region, and it really can't pack as tightly. And so what that does is semi-crystalline structure gives you kind of the best of both worlds. So you can use that to balance the properties. And we do that in pipe resins. That's why I said they're very highly engineered just for this resin. So we get the stiffness and strength from the crystalline region, but we get the flexibility, impact resistance, and even abrasion resistance from the amorphous region. So you control the percentages of each of that utilizing these different chemicals, and that's how you end up with polyethylene pipe grade. And the fourth generation polyethylene, PE4710, as we talked about earlier, is really good about how to place all these in the right place in the chain to get the best performance characteristics.
I don't want to upset Dan too much because I know he wants to get into the whole electrofusion part of this deck. But, Stephen, when somebody like you says the chemicals and we're carrying water, drinking water in our pipe, we're not PVC. We're not that kind of chemical. I've been taught that we're hydrogen and carbon. So what chemicals are you talking about? And are these hydrogen carbons chemicals?
Well, I guess, as a chemical engineer, I guess I do call those chemicals. So you're right. There's not a lot in polyethylene. It's a very clean process. So it is almost only carbon and hydrogen that's joined up into these structures, if you will. So yeah, I appreciate your clarification on that. We don't have a lot of chemicals that are just thrown in there. I was talking specifically about ethylene and the comonomer that's thrown in there, which is usually like hexene or butene, something like that. Another very short carbon chain, carbon and hydrogen.
When I talked to Doug Keller about this, who's been on this program quite a bit, he says that any chemicals we add are food grade chemicals. What is he talking about? What does that mean?
So there's a lot of things that we have identified, as you know today, as things you would not want to ingest. There's a lot of chemicals in our environment that you don't want to touch, you don't want to ingest. So food grade chemicals are ones that have FDA approval, means they can have food and water contact, and they have a allowance of how much you can ingest of those, and will never be an issue for you. So I would say everything's a chemical. I mean, every organic thing is made up of a chemical. So there are ones you like to eat and ones that you don't want to eat. And polyethylene doesn't have any of the bad stuff that you would not have, that you wouldn't even allow in your food or contact or anything like that.
Thanks for clearing that up for me.
Yeah, good point. Thank you. So what makes polyethylene a fusible material? So again, it's because it's semi-crystalline in nature. It's the way that it melts and reforms because it's a thermoplastic. So thermoplastics, you can melt many times, reform it, and cool it, and it will have no damage and still retain all of its original properties. A thermoset material, such as a fiberglass epoxy type grade material, something like that, once it joins and cures, you can't pull it apart. You can't rejoin those molecules later on. They are the way they are. So polyethylene you can redo multiple times, and that's what gives its ability to be fusible. So these molecules, the nice thing about polyethylene is it wants to join to itself. What joins polyethylene together, here's another chemistry term for you, is its van der Waals forces evolved around those different ions. So those different hydrogen and carbon ions they want to join to each other. So these van der Waals forces pull them together innately. They want to do that. And so that's what makes polyethylene uniquely fusible from that standpoint. So that's what allows us to do butt fusion, electrofusion, socket fusion, and a saddle or sidewall fusion that you all see. They all use the exact same mechanisms. They use melting, they use force, and they use cooling of intimate surfaces to get that molecular bond between the two. It's not really a bond, it's an interaction. So actually intermingling of these molecules. So it's not like they're bonding together, they're intermingling together to give you that monolithic structure.
And Stephen, you have a few more slides, but I just want to interject because to me, we're not just going to the chemistry because it's good to learn about chemistry. That all adds up to the selling proposition of being a fusible system. So while today we are covering electrofusion, Stephen's really just telling you all of the math and science that goes behind fusible system and how it works. We're not telling you that butt fusion or electrofusion, where to use them. We're telling you it's another great solution. And, like you alluded to, Stephen, that socket fusion, saddle, sidewall, that's all valuable too. We'll go through some of that in the cases this afternoon. But that's my main takeaway here is a fully fused system regardless of the fusion mechanism. And that's all the science behind it. So thank you.
Yep, absolutely. So, like I said, the polyethylene wants to join to itself. Once it's a clean surface and you melt the surfaces and you touch those surfaces together intimately and get that intimate force between them, they want to intermingle. So it works really well, actually. The only thing that doesn't work well is if you get contaminants on that molten surface before you bring the two surfaces together. That's the only thing that can then potentially get in the way of having a good intimate bond and a monolithic bond that won't come apart. They'll be as strong as the pipe itself or as strong as the material. So here's an instance. These are a few pictures of some things that could happen. These are all electrofusion situations. So the one on the top left where you see the bubbling, that's likely because there was moisture in the interface. There's either moisture in the resin of some sort, in the pipe or on the fitting, or just in the interface itself when it wasn't cleaned properly. There could have come from a number of sources, but if you see something like that, that's because the moisture was in there. When it heated up, it volatilized and caused little bubble surfaces in the molten polyethylene. That would be a bad situation.
And Stephen, we do roadshows. I love telling people that one of my personal favorite things about polyethylene is it's a very visual material to work with, right? So you get all these different visual cues when you're butt fusing, when you're moving it around above ground. And I think that is why electrofusion is perceived as being more difficult, is you lose a lot of the visual cues, right? You can't get your head inside of an electrofusion coupler to make sure it's going well. So when we get through the process, that's why it's so important for that quality control to be there, because the corrective action is more difficult, I think, on electrofusion.
You're right. Yeah. And that's why with electrofusion, surface prep is so important. And I know we'll get into that a lot more later on. And here's some situations why. You can see on the top right, you can see some contaminants inside there. You can see some dirt. You can see there wasn't bonding from the electrofusion coupling, the electrofusion process when it became molten and pressed together. There was too high level of contaminants and it couldn't bond. Same thing in the lower center picture. You can see there where you just did not get good bonding. You can see the wires where the actual molten process happened. You can see some bonding, but you can also see that it wasn't cleaned properly, and that's going to interfere with that electrofusion process. So you're right. You won't be able to see it afterwards as much. There are a few other telltale signs you can look for to make sure you have a proper process, but you can't see what's going on inside of the fitting. So that's why surface prep is so important. So heat fusion or electrofusion is when polyethylene, when you free the polymer's hands, you're really not freeing the hands. What you're doing is you're freeing the structure, right? So you got this semicrystalline amorphous regions that are all locked in place. You're adding some energy to it, and that takes it above its melting point. And now you got this viscous fluid, if you will. So now it's a material that can move and flow very easily because it's molten at this point. Not like water, but it does have a very high viscosity, but it can move. So as long as there's no contaminants in the way, that material does want to bond to itself. So as soon as you bring those molten surfaces together, because they're free to move, those intermolecular entanglement is going to start to occur automatically. That's just what it wants to do. Now, not all polymers are that way. There's some other types of materials that do not want to bond itself very well. So just because something else might be heat fusible, it may not be the same mechanism. So don't confuse that when you see it with polyethylene, this is the way it works with polyethylene, and it's very forgiving with polyethylene because of this. So it's temperature specific. You got to have the right amount of time, the right amount of pressure or intimate mixing and intimate holding of time. And then it has to cool under that pressure so it doesn't pull apart when it starts to solidify. So all these things have to happen at the same time to make sure you get a good permanently monolithic joint. And that takes us then specifically into the topic of the day, electrofusion.
Fantastic. Great job, Stephen. Really appreciate your in-depth analysis and explanation of this stuff. All right, Dan, back to you.
Well, once you get me started, it's hard to stop. All right, thanks, guys.
Awesome. So that's the feasible approach. Thank you, Stephen, very much. Bill, if you want to come on, we'll start actually going through the specific steps, procedures, process involved. with
Right.
Electrofusion. So you do the training, Bill, right? I mean, you're a salesperson, but you do hands-on training and giving certs, correct?
I have been for many years. Yes.
Okay. Awesome. Well, I'll let you do your thing. And if you want me to come on and add to anything, I'm here, but take it away.
Right. So, starting with what we have on the screen here today, the process of making a fusion, whether it's a butt fusion, socket fusion, electrofusion, involves three parameters that we need to know: temperature, time, and pressure. The temperature relates to the heat that's generated to melt the pipe and cause that molecular bond. Time is whether the time necessary to make the fusion happen and the time necessary to let it cool properly. And lastly, the pressure, which causes the molten polyethylene, as it relates to electrofusion, the molten polyethylene between the coupling and the pipe to mix. As that mix occurs and then cools, that's what makes a fusion happen. To continue with making the process of the fusion, we need an electrofusion processor. And then the picture on the right, we have restraint clamps. So we're holding the pipe ends and the coupling stable. So while it heats and then cools, there's no movement between any of that. It's a solid, fixed scenario during that full process. Electrofusion, at its most basic, involves the introduction of a controlled voltage to a heating coil, like you see on the picture right there. That coil, once it gets hot, causes the plastic in both the fitting and the pipe to melt. When they eventually cool, those molecules have mixed and they bond together, creating a joint that is stronger than the pipe itself, just like you'd get with butt fusion, socket fusion, or saddle fusion.
So we got a great question, and I usually put information in here to address this, and I did not for this presentation, so I'm just going to give it to you.
Okay.
One of the guys in the Q&A function, you guys ask us whatever questions you do have, but he's concerned about does the clearance or the angular space between the coupling and pipe, does that matter? Is that an engineered amount, and how do we account for that?
So it does matter. You want that to be the least amount of space, of annular space that's possible. Maybe 7/100ths of an inch or 7/1000ths of an inch. You want a very snug fit as that coupling slides over the pipe. Additionally, polyethylene pipe, as a part of its flexibility, also means that it may not be perfectly round. So a part of the preparation is to add re-rounding clamps or to use re-rounding clamps on the pipe to return it to a proper round shape. After that's been done, it's easier to slide the coupling over the pipe and make that connection. So yeah, the annular space should be the least amount possible.
Yeah, totally agree. Thank you, Bill. And the other thing that I've heard is that the Electrofusion couplers and pipe are both manufactured at 73 degrees. So a lot of times when I hear this question and then I get out and talk to guys like Richard Oaf, and it's like, hey, what did you end up telling those guys? And it's, if you keep an Electrofusion coupler in the middle of the winter in your car or in your truck at work, and then you get out and try to do the fusion, that coupler is going to be acclimated to a different temperature than the pipe outside. So I've heard the best practice is actually to go take that coupler, put it right down next to it in the trench, and let it get acclimated so that they are, expanding and contracting at the same rate.
That would be correct. You want to keep those two products as close to the same ambient temperature as possible. That should ease the installation process when that comes about.
Awesome. Thank you, Bill. Didn't mean to interrupt. Continue.
It's all good, Dan. So digging deeper into the actual fusion process, the electrofusion coupling, where it has the electrical coils, heats an area that is called a hot zone. Outside of that hot zone, both interior and exterior, is an area called a cold zone. That cold zone does not melt. It keeps the hot zone and the molten polyethylene constrained and forces it to mix. So the molten pipe material and the molten electrofusion coupling material are forced to mix because you have those cold zones outside of that hot zone. Circling back, we're talking again about keeping everything stationary. Alignment clamps or restraint clamps are used during the fusion process. Any size coupling or any saddle, that's important that you have those in place. You don't want any movement whatsoever during the fusion process or the cooling process. Prior to starting everything on the fusion, you want to make sure you have cleaned the pipe. That involves removing any contaminants that are on the outside of the pipe. A contaminant is anything that is not polyethylene, and later after it's been prepared, virgin polyethylene. So we want to remove rocks or any kind of debris that's impregnated into the pipe just from the work environment. And then we want to clean any contaminants, whether that's oils or oils from your hand or what have you. We mostly do that with isopropyl alcohol, and we're cleaning the outside of the pipe to make sure there's no other contaminants in place. We can't emphasize that enough. Marking on the pipe, we want to use a non-contaminating marker. So no paint pens, no grease pencils. Ideally, it's a silver Sharpie. It's visible on black and yellow pipe, and it does not contaminate the fusion area. So the clean zone, before we scrape or peel the pipe, we're going to mark the area that we're going to scrape and peel by using that silver Sharpie. As we peel it, we're removing approximately 7/1000ths of an inch of pipe, about the thickness of 2 sheets of paper, and we should be removing that marked area. That tells us visually that we have scraped or peeled the area to what our expectation is and exposed virgin polyethylene in preparation for installing the coupling or the saddle in that area. The tools necessary to scrape or peel the pipe are engineered for that purpose. So we have a picture on the right, or in the center in this case, that is a manufactured tool designed to peel the pipe. The picture on the left shows manual tools that are being removed from the standards and being removed as recommended tools to use in this instance. We want to avoid those as much as we can. And then on the right, no sandpaper, no utility cloth, no emery cloth, no wood rasps, definitely no metal files. You want to avoid using any of those on the job site.
Hey, Bill, we're getting a lot of good questions in the chat. They're very specific, so I'm glad that all the manufacturers are on here answering those. But do you train inspectors as well? Do you train like utility inspectors so they know and they're making sure the contractor, as they audit it, is following all these procedures correctly?
We would put an inspector through a fusion training class itself so that they understand all of the principles involved in making those fusions, and then would help them add inspection criteria to their existing inspection processes. We don't have a specific inspector-only training class. So continuing here, electrofusion tapping, the preparation necessary for that. And for what it's worth, electrofusion saddles can be a tapping tee, or they can just be a saddle that you would you drill through the pipe to create an outlet.
It's like a little video show what that process looks like. They're down on the trench, Bill.
Yep.
I like the rotary peeler. I'm a big fan of those.
That's a great tool. It can be adapted to many diameters of pipe. It's easy to use, and it gives you a great visual cue that you have peeled or scraped the pipe completely.
Yeah, and I got one more video, Bill. You could talk us through, please. But I think these videos, to me, they demonstrate why electrofusion, the cleaning is so important. Butt fusion's typically happening above ground where, yeah, you have to worry about dust and debris. But I think almost every single electrofusion we show in this presentation today is in the trench. A lot more difficult to keep things clean down there, 14 feet below ground.
It is without a doubt. As you look at this video right now, this peeler rotates around the pipe, does an excellent job when removing material. This is a hand scraper. Again, we're trying to move away from that in the industry. The electrofusion coupling in this case has been left in the bag, keeping it clean and protected. A little bit of assistance putting the pipe or putting the coupling on the pipe. The electrofusion processor has been attached to the coupling and the barcode is being read.
How long do you typically have, Bill, on those leads to get down into the trench? So here it looks like their processor is actually above ground. Was that about 12 feet before you had to put it down?
I think each one's a little bit different.
Okay.
I believe ours are 6 feet long. As long as you're keeping it out of a wet and moist environment, so you don't want, if there's water in the trench, you shouldn't be doing the fusion anyway. But because it is an electrical process, you want to stay away from water in the trench. Or water above ground too. Circling back to restraint clamps or assembly clamps, we have an example for an electrofusion coupling on the left. It restrains the pipe so there can be no movement during the fusion or the cooling. The image on the left is an underclamp that's going to be used on a saddle. There are many different styles of underclamps, but again, it keeps the saddle clamped to the pipe so there can be no movement whatsoever while the fusion is happening or in the cooling process. So the fusion parameters are controlled. They're essentially processor controlled. What we want to do is read a barcode, and it's a generic barcode. So it's an agnostic system between any processor and any fitting. That barcode is read by the processor, and it will determine the fusion parameters: the time, the temperature, and the pressure. Those 3 parameters can be modified with a manual entry, but we don't recommend that at all. The barcodes have been designed by the manufacturers for that specific fitting, and a modification may compromise the quality of that fusion.
Yeah, and I have a slide later, Bill, that, one of the cool things about electrofusion is the processors, they can all read each other's barcodes.
Yes.
So don't be concerned if you have an integrity processor and you have, George Fisher fittings or Strongbridge fittings or Nupi fittings. It doesn't mean you can't do the fusion. They interact well, right, Bill?
You're correct. And in fact, you're showing the barcode structure right now. That's an ISO standard that creates that barcode. Let's see, the first set of numbers is going to be the manufacturer's indication, also determining cooling time. And for whatever reason, one manufacturer may say, we want a 10-minute cooling time on this fitting. A different manufacturer may say, we want a 15-minute cooling time. So that's up to the manufacturer to determine some of those parameters, but the barcode itself is an international standard. Processors read each other's barcodes. Power requirements. This is a good chart to have, but I will simply say use a solid generator, not a welder, and not some old rickety generator that's been riding around in the back of a pickup truck for the last 25 years. Good, clean, solid power is important. Also, turn off any auto idle feature that would be on the generator. You want it running at full RPMs when you start the electrofusion process.
Awesome. Thank you, Bill. I'm going to move on, but if you want to stay on, I know you have a whole lot to say about some of this stuff, starting with a point that I just made, and that is that the product manufacturer, so if it's a coupler or a saddle, whoever makes that, it is going to be compatible with the equipment.
Correct.
Now, on the training end, one thing I do want to make sure people are understanding is, whereas George Fisher, they're going to accept Nupi's training, and Nupi's going to accept Strongbridge, and Strongbridge is going to accept the next guy. It does have one component to it, and that is going to be the fact that the trainings do change based on diameter. So
Correct.
I don't know, Bill, exactly how do you guys give your training, and what does that look like? I know the MAB standard changes over at 12 inches. Does your training follow that same categorization?
So we have a training category, level 1, that goes through 12-inch. Level 2 goes through 24-inch. We then have a level 3 that is 26-inch and larger. Now, level 1 and level 2 we will accept other manufacturers' trainings, and we base our training off of the Municipal Advisory Board MAB 01 and MAB 02. So we do expect that if somebody has been through a training from a different manufacturer, that content has been presented to them and they're familiar with it.
And on that large diameter stuff, you guys won't even sell it without verification of the installer having been trained, correct?
Completely correct.
Okay.
Completely correct. We then go to a larger diameter level 3, which is our larger diameter couplings. We do that training at our facility in Jacksonville, Florida, and it involves the special tooling to make that happen. Also large diameter saddles, which is level 4. That also requires special tooling for installation, and there are some pictures of that later in your slide deck.
Awesome. So here's some of the guys that do offer training in the industry. Shout out Ben for being on the Q&A today, answering all your questions, and for Bill doing it live. Very helpful. These are all the facilities, but a lot of them will come to you as well and get you guys trained in the process quickly.
Right.
So this was based on integrity. When I came into the industry 5 years ago, I did small diameter training, L1. So that L1 follows the MAB 01, which is up to 12 inches. That you'll get a certification that looks like that. So if you're an inspector, this is what you're asking the qualified contractor for. This is what they have to be able to provide. If you let me take a look at your specification, I will require that your Electrofusion happening on your project is by a qualified tech, and there's a whole bunch of language that goes along with it. But this is the deliverable. They also, the manufacturers will print you out a driver's license basically saying what diameters you're able to do up to. My large diameter training was with George Fisher in Shawnee, and I believe I'm only trained 14 to 30 inches. But like you mentioned, Bill, there is going to be an additional training on that, anything larger than that 30 as well.
Great. Thank you.
Yeah, thank you, Bill. So there's a few different situations where I think Electrofusion is just a fantastic fit. First and foremost, repair. We've gone through this a bunch. Another great PPI document is MAB4. And whatever you're currently dealing with on that repair setting, they have these great decision trees that you guys can work through. Our opinion is the only thing you can put back in your system where it's not going to limit it and you're going to keep that fully restrained monolithic approach is to do an Electrofusion spool repair. So thank you for everyone who got on the call early. You were able to see that, the 10-minute demo that Rick and Max Yelkin did at Integrity. But it's pretty simple for the most part. And Richard and I are going to have some cases this afternoon of what this looks like in the field. But you have a damaged section. Maybe it was a backhoe, a crossbore. You didn't know a location of a service when you're digging for it. But just keep in mind, wherever a new Electrofusion coupler is going to go, we want to make sure we're prepping that. We don't want any type of cross-contamination on the outside of that pipe and the inside of that coupler. So when we slide that coupler on, not a big deal. We're good to go. And then you're going to situate and fuse. This probably does take a little bit longer than a mechanical connection. And there are a lot of great mechanical approaches out there. You can see this is a very nice trench. There's relatively little groundwater. It's not raining. But yeah, fully fused, monolithic, all the selling propositions for polyethylene are maintained when you guys are going to be using Electrofusion. And service connections, Brian Swanson, if you're there, I think he was going to come talk me through a little bit. He has a lot of experience, right, as an owner, a specifying engineer. Brian, I always tell people, I think from left to right, this is your best adoption. I think Peter put this sample together, but I think it does show, somebody going from, I don't trust poly to I'm all in, fuse everything.
Yeah, and we're looking at the tapping saddle side of things. So in any, residential type installation, and these are representative of those, so say 3/4 inch to 1.5 inches, something for a typical residential service. And you'd have the tapping saddle, and then the corporation stop, and then a curb stop, and then your meter crock and the service to the house. And so we're really looking at the tapping saddle side of things. And in going kind of from left to right, you have a mechanical saddle with a curb stop so that you can do a hot tap through the main. One thing about this is it's not completely fused to the polyethylene, and the more you want a fully rated pressurized system, the more you want to have everything in the system be a fusion joint. This is a place where people can start, but the clamp will have a tendency to move around over time, just due to the pulsing of the polyethylene line, and move up to an Electrofusion branch saddle, which you can fuse something else onto that. That in and of itself right now is not really set up to do a hot tap because it's just a pipe that's going to go through into your main. And the next level of kind of adoption would be having the Electrofusion saddle, second from the right, where you then would still have a corp stop on it. And you can see at the very top of that corp stop, there's the ability to compression fit a pipe in there, either copper or polyethylene. And in our industry right now, really the only major lateral types are polyethylene and copper. There's some PEX thrown in there depending on your area of jurisdiction. But with that corporation stop, you would be able to drill with a tapping tool directly through and make a hole in the main and withdraw the cutter head past the corp stop, shut it off, and then once you put your lateral on there, you can throw the corp stop again and go live. On the far right hand side, we have everything that's electrofused, and that would be the Electrofusion tapping saddle, and then an integral tapping key that's built into that saddle. And so you take that end cap off, and with a hex key, rotate a cutter down, make the penetration in your pipe. The cutter head will retain the coupon up in there, and then you're live. So you can just directly tap. And the corporation stop, you're really only going to ever use that once, and that's when you're hot tapping a line. With polyethylene laterals, you can also do squeeze off. So you really don't have that extreme situation where you're getting down and you need to access that corp stop and shut things off anymore. So that's a good way to save, a couple $100 on a fitting, is to just not have those. And really, if the customer doesn't pay their bill, you're going to go to the curb stop or that valve that's usually at the property line and shut them off there.
Yeah, all great points, Brian. I kind of always tell people when they come to a roadshow and going into services, that's like something we get really deep into the roadshow. So I encourage anyone that can come see us live. It's a great presentation we have. But there's a lot of developers. I was looking through the registrations. We have a lot of developers. We have a lot of utilities, a lot of specifying engineers on today. But more developers than we normally have. So I know I'm speaking to the right audience. I personally think if you allow the contractor to do whatever they want on the services end, you're most likely going to get a mechanical saddle with a brass connection to anything from copper or polyethylene. So the only reason I mentioned that is by not making a decision exactly how you want to do your services, I'm just letting you know what you're going to get. In the same way that if you don't specify an MJ, there's a good chance you're going to get a mega lug just because they can make that connection a little bit quicker. So we're not really here today to solely focus on service connections, but I do think Electrofusion is a great approach if you want to go from a threaded brass connection to a copper, however you're doing it. It's going to give you a whole lot of options. And like Brian mentioned, that right-handed self-tapping tee, that's going to give you no metallics in your system whatsoever. We think that's the highest level of adoption, and that's what we push. But we do know, everything else happens in the field. So if you want to have a good conversation, reach out to your local distributor. They can help you, really take a look at specific connections, and we can help you guys get standard details and get that spec however you would like. So once again, showing what it looks like in the trench. This is a live tap using a traditional tapping tool. Unfortunately, the self-tapping tees are only good up to about 10 or 12-inch mains. And then above that, we're using regular tapping technologies that are available in legacy piping materials. Definitely come out to roadshow, put your hands on it, reach out to your local distributor, have a conversation with them on kind of, where you are in your adoption, what kind of trust you guys have in your contractors, what does your spec look like? That's all part of a continuum, and we're definitely here to help. You don't have to make any of these decisions on your own. I'm just going to emphasize that one last time. By not making a decision, you're probably going to end up getting the mechanical saddles with metallics. If you're okay with that, great. But if you would rather have a fully fused monolithic system all the way to the service, we can help with that as well. And sometimes they do the brass. This is only one component away from being fully fused. If they would get rid of that connection there, right? 'Cause like Brian mentioned, you can always squeeze off and cut off service if you need to in other places. So what does it actually look like in the field?
Inside of that connection there, Dan, and the Electrofusion saddle actually has a thread embedded in it to enable you to screw that corp in there.
Yeah, you're right. Those are very nice. So real plug and play in nature, kind of getting to the benefits of a mechanical system, but still having that fully fused onto the pipe itself. So why is preparation so key? Well, these job sites are not super clean all the time. I think this is the exact same setup, Brian. They're gonna tie in that tool right onto the thread, drill down like you would with PVC, get out your corp. Loosen it up, take it out. And once you start shut that back off, you'll have a live tap continue on with your regular service line. So there's a whole lot of options. We're going to move on, just talk about some of the other benefits of Electrofusion. But for service connections, particularly if you're going to go HDPE, I really recommend that fully fused Electrofusion coupler. So thank you, Brian, for joining us. Richard, if you want to come on, I really appreciate you and your team sending me so many great cases. I had to work through these myself, but yeah, a whole lot of different ways to use polyethylene. The first is a really cool project. We talked about this a couple times, but this was in your territory down in Arizona, going from a man-made lake. This is a canal conversion, and as they were lining this canal, you can imagine the fusion zones are very far apart from the laydown area and staging area. So when you actually look at doing taps, you could have always, fused inline a T, right, Richard? But it's more difficult to drag a string with a bunch of T's on it correctly into place.
Yeah, that's correct, Dan. As you pull the pipe string, they tend to rotate or twist. So the odds of having that T line up specifically where you want it, it's a little difficult. So this application is a much smarter application.
Yeah, and getting all those locations correct from the beginning on pipe strings under 3,000 feet can be quite difficult. So what you guys went with here, and Bill, I know you're going to have a lot of comments on this setup. I was actually out on this project and I didn't see any connections quite this large. So it looks like they have a saddle for a live tap, or probably not a live tap, but a large sidewall saddle. I've never seen this setup. Can you walk us through this a little bit, Bill and Richard?
So this is it is a large diameter saddle. It's a Tega brand from Strongbridge, and we're using the spider tool to hold the saddle against the main pipe. This instance, that saddle is coming off the pipe at a downward angle, about 45 degrees down. And we had to use the saddle both to hold it against the pipe and to keep it from falling away from gravity. So it was serving a double purpose in that case. On either side of the saddle, you can see re-rounding clamps. Those are hydraulically operated. So we're making sure that the pipe is as round as it can be in that case. So the base of the saddle, the concave base of the saddle fits against the convex surface of the pipe. We wanted that to be as secure as it possibly could be.
So are those pump jacks on those rerounding tools? Is that a hydraulic tool?
It's a manually operated hydraulic system. Yeah.
Okay. I have not seen those before. Another large diameter project Core and Main did. This is, I believe, in northern Minnesota. Can you guys walk us through this setup? I've never. What is this orange tool doing exactly?
It's called a spider tool, or maybe a spider clamp, but it's specific to our product, and it's designed to apply force to keep the saddle on the pipe during the heating, fusion, and cooling process. So it's required when an outlet on a saddle is 12 inches or larger. And again, it's specific to our saddles. There are 3 pictures there that show that in place and being used. That is specialized training at our facility in Jacksonville, Florida, to be able to install those saddles and use that tooling.
Bill, thank you for bringing that up. I assume this is your L4 training.
That is correct.
you guys do a fantastic job with this. A few years ago, I did a video of you guys doing it, and I can see why you want to make sure people that you're selling your products to are properly trained, because this is a boutique, this is a niche skill that not a lot of people have.
Right? There are very few people in the country who have been through this training and have this capability. So,
Yeah, so good work.
Yeah.
What's great about this application too, guys, is these irrigation lines, if the customer came back and said, hey, we want to add a turnout, an air vent, or anything, it can always be added as a future item to an existing line. So it's a great product.
Correct.
Yeah, it does not limit. That's really important. Richard, here's another great one. I think Caleb, the Southwest Corn Main guy, sent us these. I guess you could use a butt fusion with an Acrobat, right? You could have put that down there up to 20-inch.
It's possible, but this is a much more feasible application because we were able to build these risers coming out to the length to daylight, and then tie them together with the Electrofusion coupling. So this is a much faster and practical application than trying to lower equipment down in there.
Yeah, we were on the call beforehand, and Alan said, we've been looking for a picture of this for quite a while, so I'm glad you guys had a good example of doing that. Now, this is just saving you from having to put heavy machinery right down that lift station, but a lot of times it's really, I like to say, geometry limiting, space limited. And here it's kind of hard to even see where the couplers are because it's so dirty. But would you manufacture these as spools, or would you just start cutting things to size in the field as you fuse these together, Richard?
That probably depends on the application, Dan. As you're building your way into a corner or into a head wall, sometimes these things pop up. So in this application, that's exactly what happened. They had daylighted pipes with the intention of coming back and doing butt fusion. But once the concrete was poured, it just wasn't feasible to get a machine in there. So we turned to Electrofusion.
Yeah. So once again, a great tool in your tool belt. This is just very difficult proximities to do any type of Electrofusion in there. And I'm sure there's a lot of callers recognizing that clay. That is a power plant in Georgia. So very cool application. This was a new one for me, Richard. I have not seen this tool before, but I mean, the worst part, in my opinion, of Electrofusion is having to deal with scraping. It does take quite some time.
Yeah, it is truly a labor saver, and it's awesome. This application was, as you can see, the pipe was daylighted, but it came out at an odd angle once the structure was in place. And to the right of it, where the sledgehammer is laying on the pipe, we just were once again out of space to put a large butt fusion machine. As I think that's a 30-inch. But so once again, we prefabbed a fitting to make that offset, and then tied it together with two Electrofusion couplings.
Yeah, and this is like, to me, Richard, this demonstrates why, regardless of which distributor you're using, where you are in the country, it's so important to have a good relationship with your local distributor, because this is just a tie-in. What is the problem? Okay, well, we can do that with a fabricated offset, tie that with some Electrofusion to make that connection pretty easily.
Yeah, that's when you have.
Sorry, go ahead, Richard.
I'm sorry, Pete. This is what happens when you have an experienced technician that's in the field that's able to pull that off instead of just trying to power through from a contractor point.
I love this slide, Dan and Richard. Thanks for bringing this one in, because here we are using a spool piece to connect two pieces when the ends just don't line up with each other. And, we've made this joke forever, Richard. I think you're the one that started it. And that is, hey, if you can draw it on a napkin, we can fabricate that spool. But sometimes they don't know what the distance is and the geometry is when they're doing the work.
No, that's correct. And sometimes it just doesn't pencil out like the plans look. So we often pull it out of our lunchbox, we'll say, to get it.
I like it. So, okay, this is a big differentiator, Richard, and you guys put this together for me, and I'd not really thought through this before. here you guys see a spool piece being dropped in between the two couplers. So we're doing electrofusion on both ends. But then on this next example, Richard, we have over here, we're doing one flange connection on the right and then one electrofusion coupler on the left. Would you say that's pretty common as well? What is the benefit on doing one side flange instead of, doing both with an electrofusion coupler?
So oftentimes there's a valve that's been added, or maybe a pipe was damaged that was attached to a valve. So we often will take the flange adapter and put a small spool onto it and then tie it into the pipeline, so you are able to extend your pipeline and still keep your valve in service.
Okay. And it looks like here on that spool piece, I've never actually seen this before. They're dropping a valve down of some sort as part of that spool assembly. Very cool.
Yeah, that's pretty cool stuff right there. There's a lot of money in that little trench right there.
Yeah, you can mention that. But yeah, so to me, the whole theme of today is these electrofusion couplers, whether it be access limited or you're kind of just doing something that's building, power plant, a water system, whatever you guys are working on. Here's a cool one, Richard. They actually had to do a jumper line to do flushing at the end of 42-inch headers. This was on a geothermal project right here in Pittsburgh. So this is a pretty cool one for me to see. And I don't know if you can tell, but they actually did 2 sidewall fusions to get off of the main chiller lines and then connected them up and over with electrofusion couplers. So that probably would have been a spool piece out into the field, right?
That's correct. Yeah, and they actually came into the top wall of those spools, which those with the large diameter, that could be a flange, the body of a flange. It could be part of an elbow or a T. As long as there's meat on that fitting that we can get into, we can pop something like this on. It doesn't have to be specific to a straight piece of pipe.
So they told me that this was a temporary jumper line just to flush it, and then it was removed after. And they said they fused end caps back on. Is that a butt fusion if you were going to do an end cap? Or would that be an electric as well?
I think we're limited to size, but it could be either. There are electrofusion butt caps or termination caps, and there's also a butt fusion cap. So once again, probably just depending on what your space is and what the size of the pipe is.
Awesome. Okay. Yeah. So the next example, this is a user submission, and I've got a handful of these recently. A cool project, most recently 2 weeks ago from Ontario. There's a handful of these. So when they do microtunnels, you have shafts on both ends, and I think these connections are great options for electrofusion. You've tight proximity, you're 35, 40 feet below the earth, and the engineer may allow mechanical connections. The last 3 or 4 I've worked on have required it to be a fused system. So they just did not allow a mechanical tie-in to that. So once again, size, it is going to be more difficult being a 30, 36-inch line in the ground, but the amount of equipment and people you're going to need to get down that low, it's really beneficial, if at all, we can keep it fully fused. We don't want to be having leaks 30, 35 feet below the ground. So just getting people's minds thinking about when these are great applications. And Richard, I haven't seen this one yet. Is this common, using a coupler to get a MJ adapter stub end on?
Kind of like what we were talking about before. This is probably either a transition into a different type of material like ductile, or they are adding a valve. So they cut the HDPE, used a pup on the MJ adapter, and then stabbed it into that electrofusion coupling so that they could make their transition, whether it's a valve or into a foreign piece of pipe.
So you think they had to cut into a line that was already in the trench, and it was just easier to put a coupler on it than a butt fusion equipment?
It could have been a cut-in, or it could have been by design, but once they got to the end of that line, they realized that they didn't have room for the butt fusion. So it could be a new application or a cut-in, but either way, it's a perfect application.
Okay. Awesome. Yeah, and then the last one we had is you will get flexor strains offer you a whole lot of flexibility in the field, no pun intended. This is an example of a harness. This is a specialty restraint coupler that Robar makes. But on the first picture, you can see to actually get the restraint, so these bolts are pulling across each other and they are being restrained by flex restraints. So these flex restraints right here, you can see in a row, all of these in line, that's providing the resistance for these couplers to be able to work. So we didn't really talk too much about flex restraints for anchor blocking, but flex restraints, when you're tying on things to polyethylene, regardless of what it is, it'd be a restraint coupler like this, or maybe concrete weights to hold the pipe down. Flex restraints can be really useful as well. We're always really interested in see how people are doing them in the field. So that's all we had for prepared comments today. Richard, in your experience out west, are people using more electrofusion, or are they still using mechanical saddles on service connections?
Probably depends on what the meter service is calling for. We like to see as much electrofusion as possible because we're keeping that monolithic system from A to Z. Once you introduce that mechanical fitting, you're just, slightly weakening the system. So any chance we have, we try to encourage using completely fusible system.
Fantastic.
I'd like to add too, guys, great job on today's deck, that electrofusion is, I've heard, more popular in Europe than butt fusion. Yet in the United States, we tend to do more butt fusion than electrofusion. And I really like, Richard and Bill, your emphasis on the importance of training and preparation. Dan, great deck in that regard. I mean, to me, that's like the key message, preparations and everything. People like to criticize us that, we need machinery, we need preparation, we need training. And it's so different than just putting the bell and spigot together. But when you do it correctly, you end up with a product that's going to last hundreds of years. And that is the beauty of HDPE pipe. Not only does it not leak, it's going to last much longer than legacy materials.